Hello everyone, welcome back to Easy Talim. Imagine you're sitting in your Cambridge examination, you turn the page, and the very first thing you see is this that you want to solve for x. 2 to the power x is equal to 10. Now, don't solve it. I would say that you just stare at it for a few seconds. Can you solve it? Most students immediately start guessing maybe x is equal to 2. Then 2 power 2 is 4 and not 10. Maybe x is equal to 3, but then 2 power 3 is 8 and not 10. Maybe x is equal to 4, so 2 power 4 is 16. Now, so the answer lies somewhere between 3 and 4, but Cambridge doesn't want guesses. Cambridge wants math, right? Now, here's something interesting. Let's look at equations you have solved your whole life. Now, if you have x plus 5 is equal to 11, how do we do it? We subtract 5 from both the sides, right? And you get x is equal to 6. Now, if you have 3x is equal to 18, how do you solve it? You divide by 3 on both the sides and you get x is equal to 6, right? Now, this is easy. Now, what if you had x squared is equal to 25, right? How do you do it? You take the square roots on both the sides, so you get x is equal to 5. If you had, I don't know, if you had, let's say, x cubed is equal to 64, how do you solve it? You take cube roots on both the sides, so you get x is equal to 4, right? We have an operation that reverses cubing as well, right? So every operation you have ever learned has an opposite operation. For addition you have subtraction, for multiplication you had division, for square we have square roots, for cubes we have cube roots. However, for exponentials 2 to the power x is equal to 10 had no opposite. That was the problem, and this problem existed for centuries. So mathematicians had a question: how do we answer 2 to the power x is equal to 10? The problem existed for quite a few centuries without guessing, because guessing 3.1, 3.2, 3.3, 3.31, this isn't mathematics. There had to be a better way. And that's exactly why logarithms were invented, not to torture students, but because, and not even because Cambridge likes difficult notations, but because math needed the inverse of exponentials. So today's lesson isn't really about logarithms. Today's lesson is about inventing a brand new mathematical operation called logs. Okay, this you would find in your calculators as well. Now let's make the problem even worse. Suppose I ask you, what is the value of x for 5 to the power x is equal to 73? Now guess. You can't, right? What about 7 to the power x is equal to 120? Pause the video, keep it like that, you will not be able to guess it, right? So there's no obvious answer. Now imagine you are a scientist, an engineer, an economist, a physicist. Guessing isn't acceptable at all, right? You need precision, you need an exact mathematical method, and that's where logarithms completely changed mathematics. So here's today's journey. By the end of this lesson, you'll understand why logarithms exist, why they are simply the inverse of exponentials, right? So inverse of exponentials will be log, and we will come to that in a bit. Okay, why they are simply the inverse of exponents, how to switch between exponential and logarithmic form. So a to the power x is equal to b may be written as log b to the base a is equal to x, and we will come to that why you can do that, right? What the base actually means. This is the base. Why logarithms have restrictions. You can't have b less than or equal to 0. Okay, and why the famous logarithm laws are actually inevitable. How do you add and subtract the logs, right? And change of base laws and all that. And once those ideas click, the rest of this chapter becomes surprisingly logical. So let's build logarithms from the ground up. Now, before we proceed to what logarithms really are, which they are just the inverse of exponentials, right? I want you guys to not be just watching this video as just for the mere heck of consuming content. Rather, you have to be taking notes, right? So bring your notebook and your pen and start taking notes. So far we have discovered the problem. Exponentials had no opposite operation, so we invented one. So now, if I write down 2 cube is equal to 8. Let me ask you a question. What's really important in this question? Is it the base 2? Is it the 8? No, not really. The interesting part is this 3, because that is the unknown we usually want to find. Suppose I cover the exponent. I write down 2 to the power x is equal to 8. Now everyone is going to immediately say that it's equal to 3. But notice something, you didn't multiply, you didn't divide, you didn't square root, you simply looked at the exponent. So today's question becomes not looking, but how do we ask for the exponent mathematically? Now, so we're introducing logarithms. We invent a brand new notation here. Instead of writing 2 to the power 3 is equal to 8, this we write log 8 to the base 2 is equal to 3. Now this doesn't mean anything mysterious. It simply asks one question: to what power? Now learn this in the manner I'm telling you. What power must this 2 be raised to in order to obtain 8? What power must this 2 be raised to in order to obtain 8? And the answer is 3. Okay, that's all a logarithm is. Now let's do several examples here. Now 2 to the power 5 is equal to 32, and we can rewrite it as log 32 to the base 2 is equal to 5. That is, what power must this 2 be raised to in order to give us 32? And that is 5. Now if I write down 3 to the power 8 is equal to 81, then I can rewrite it as in the inverse form or the logarithmic form as log 81 to the base 3 is equal to 4. What power must this 3 be raised to in order to produce 8? What am I saying is, maybe my pronunciation is not, and you can't understand that. I'm saying, what power must the base, in our case 3, be raised to give us 81? And the answer is 4. Okay, now if I write down 10 to the power 2 is equal to 100, so you can tell me that this is in the inverse form or the logarithmic form. It is log 100 to the base, log 100 to the base 10 is equal to 2. Okay, now you don't have to memorize logarithms, read them like a sentence. What power, right, must the base be raised to produce this number, right? And the number in front of the equal sign is the answer. Okay, now let's do the machine analogy, which I really love doing the functions with. So I'm going to draw two machines, right? So machine 1 and machine 2. Okay, so this is exponentials. I will write this down, right? So you input 3, your output becomes 2 to the power 3 is equal to 8. So this machine is 2 to the power x. So this is function of x is equal to 2 to the power x. Okay, now machine 2, let me make this here. So machine 2 is logarithm. Okay, so this is the inverse machine of machine 1. So if I input 8, right, it reverses the process and produces me an output of 3. Okay, so this is log, so this is going to be log x to the base 2, right? So when you input 8, so log 8 to the base 2 became 3. Okay, so let me write it down, log x to the base 2. So log x to the base, so log 8 to the base 2 became 3, and this is your answer, which was produced by machine 2. Okay, now so one machine goes forward, 3 becomes 8, the other machine goes reverses it, 8 becomes 3, right? It completely reverses it. They undo each other, exactly like addition and subtraction, they undo each other. Multiplication and division, they undo each other. Square root and cube roots, they undo each other, the squares and the cubes respectively. And in the same manner, exponentials, they undo the logarithms, and logarithms, they undo the exponentials. Now why we call them inverse functions? Remember functions from AS level. One machine takes input 3, processes it, and produces an output of 8, because the function here is y equals to 2x, right? So this is machine 1. The second machine, it takes the input 2, this is the logarithmic machine, it takes the input 3 and produces an output it takes an input of 8 and produces an output of 3, because this machine is actually, so this is the inverse function. So this is log x to the base 2. Okay, this is exactly the definition of an inverse. Logarithms are simply the inverse function of logarithms, as the heading of this section also indicated. Okay, right here. So I really want you guys to be taking notes while you are watching this video. You can pause it, take notes, and then resume it. Now, let's say y equals to 2x. So this is same as log y to the base 2 is equal to x. So this is the inverse of it, right? This is the inverse. So if this was f of x, this is f inverse of x if we just swap x and y as well, right? So notice something beautiful. The input and output have simply swapped places, exactly what inverse functions always do. Now let's return to the problem that started today's lesson. Let's say, so while we were doing 2 to the power x is equal to 10, this is slightly more complicated than if we had a base of 10. So let's say 10 to the power x is equal to 58. Now 10 to the power 1 is 10, 10 to the power 2 is 100. So x lies somewhere between 1 and 2, right? We still don't know x. But now we finally have a language. Instead of writing 10 power x is equal to 58, I can rewrite this as in an inverse form, that is going to be log 58 to the base 10 is equal to x. Now, you do understand that you can convert this form into this form and find the power. However, you are now going to ask me, how do we compute this log 58 to the base 10, right? So, we haven't actually calculated anything yet. We have simply written the answer correctly. That's already progress so far. Now, take your calculator, press log, it's going to open up a bracket, put 58 there, and there you have, your answer is approximately going to be 1.763. Have you done it? Did you get the right answer? Now, what does this actually mean? It means that you raised 10 to the power 1.763, if that's an approximate value. This is going to be approximately equal to 58, right? That's all. Nothing magical happened. The calculator simply found the exponent. Now, why calculators only have logarithm? They only have logs and ln, right? Now, these are special cases. This is base 10, this is base e. Right, it's a special Euler's constant. Now, where is log base 2? Now, you may ask me that if we have 2 to the power x is equal to 10 and I have to find the answer, so that's going to become log 10 to the base 2 is equal to x. Now, we will come to that in a bit, but not in this lecture. We are going to do that in our Wednesday's lecture, okay? Now, so log base 2 also exists, log base 5, log base 73, everything exists in your calculator, right? So far they're missing in the buttons, but we do have a method to solve this as well. We'll discover why later in the chapter when we study change of base as well, right? For today, just remember that log means base 10. So this means base 10. Okay, so if I'm writing down log 58, automatically your brain must tell you that this is log 58 to the base 10. Okay, now what if you have a base a? Because math isn't limited to base 10, right? Exactly the same idea works for every base. So if I write down 5 power 3 is equal to 125, I can rewrite it as log of 125 base 5 is equal to 3, right? If I write down 7 square is equal to 49, you can rewrite it as log of 49 base 2 is equal to 7. Oh, sorry, log base 7 is equal to 2, my bad. Now, similarly, the generic form, if I write down a power x is equal to y, right? If I write down a power x is equal to y, I can rewrite this as log y base a is equal to x. So these are inverse of each other. This one equation is probably the most important equation in today's lesson, right? Don't memorize it, understand it. A logarithm simply asks what exponent turns the base into the number. Okay. Now, if you're converting both ways, let's become fluent. I'll write exponential. You tell me the logarithm of it, right? Or you can't really tell me, so you just see if you're getting the right answer. If I write 6 is equal to 64, and so this is the exponential form and this is the logarithmic form. So I can rewrite it as log 64 base 2 is equal to 6. If I write down 3 power 5 is equal to 243, this may be rewritten as log 243 base 3 is equal to 5. Remember, What power must the base be raised to in order to give us the argument? And by the way, in logarithms, this is called the base, this is called the argument of the logarithm. Just like in sine x, x is the argument, right? So this is the argument of that. Now, let's reverse it now. What if I had given you log 64 to the base 4? Then you is equal to 3. Now you can rewrite it as 4 power 3 is equal to 64. What power must the base be raised to, which is this 3, in order to give us 64? So 4 should be raised to power 3 in order to give us the argument 64, right? Again, if I write down log 81 base 9 is equal to 2, then what power must this 9 be raised to in order to give me 81? So 99 has to be raised to 2 in order to produce 81. So I think this is fair amount of practice. The important thing is not memorizing arrows, it's reading the sentence, right? It's not, you don't have to memorize how we are converting, but understand and reading the sentence. Now there are quite a few restrictions when we are dealing with logarithms, and they are extremely logical, and you'll understand it in a second. Now, Cambridge asks something many students ignore: when does a logarithm actually exist? Now let's investigate. Can I write log minus 8 to the base 2? Now, what does this mean? What power must this 2 be raised to? What power must this 2 be raised to in order to produce a negative 8? Can this 2 be raised to any power in order to give us a negative 8? Of course, that's impossible, right? Because I ask this question again: can a positive base, which in our case is 2, raised to any real power, which is x, ever become negative? No, that's impossible. Therefore, log minus 8 to the base 2, which means that of this entire expression, this negative argument was problematic, right? So this doesn't exist. What about if we had log 0 to the base 5, right? Now if I had written, so this shows me what, that this the argument of logarithm can never be negative, right? So it can't be negative. But what about 0? So can I write log 0 to the base 5? Now this means what, that 5 should be raised to some power in order to produce me a 0, right? Which again is not possible. It can go closer and closer to 0 as you take smaller and smaller values of x. However, it's not at all possible that this becomes a 0, right? Therefore, it can never actually reach it. So this also doesn't exist. So for log x to the base a, we have seen that the restriction of this exists, that x cannot be less than 0, x cannot be equal to 0. Therefore, the only values allowed for x is greater than 0, which is x can only be positive. It can't be a non-positive number, and non-positive number includes the negatives and the 0 as well. Therefore, our first restriction is that x is strictly positive. The argument of a logarithm is strictly positive. Okay, so that's the first. The number inside every logarithm must be positive. It can't be 0, it can't be not, it cannot be negative, it has to be strictly positive. The second restriction concerns the base. Can we have a base of 1, log 1 raised to the power something in order to produce an 8, right? Not possible. 1 to the power anything can never produce anything but 8. Therefore, I mean, just think about it. What powers of 1 do? They do nothing. They just give the exactly the same output back, right? Whatever the so 1 to the power 100, 1 to the power 10 million, 1 to the power 2, 1 to the power half, it never changes. So base 1 is useless. So can we have base 0? No, because negative bases not for this course. So if I write down that 0 power 8, log 8 base 0. Now what does this mean? This means that 0 raised to the power something producing an 8. Is that possible? No, that's impossible. Therefore the base cannot be 1, the base cannot be 0, and the base cannot be negative. So we have to have bases greater than 0. So let's denote base by b. So b has to be positive, but b cannot be equal to 1, right? So today's restrictions are beautifully simple. A has to be, the base has to be positive, but base cannot be 1. Memorize them now, they'll save you marks later when we start solving logarithmic equations. Okay, now watch this part, this screen right in front of you. we will now be doing basic evaluations, and which is going to let us know that why the log laws must be true. I've written down the three laws that we study in this course of A2 Mathematics in 9709. And we will close with a Cambridge style question so that you guys see that the this lecture led to somewhere. Okay, now that we know what logarithms mean, let's become fluent in reading them. Remember, don't memorize, ask one question: what power must the base be raised to in order to produce an output? And that's it. Now if I write down that log 8 base 2, what power, so how do I read it? What power turns 2 into an 8? So 2 power 3 becomes an 8, so the answer is going to be 3, right? Very simple. Now if I write down that log 81 base 3, now what power must 3 be raised to in order to produce 81? So the answer is going to be 4. Very easy. If I write down, and I will be doing 5 examples here. So this is first, this is second, this is third, and we are going to extract 2 results out of them. So if I write down log 10, log 100, sorry, if I write down log 1000 base 10, or if I just write down log 1000, that should tell you that this means log 1000 base 10. If there is nothing written here, then you must understand that the base is 10. And similar to if I write nothing here, you will assume this to be square root of a, or you will write down a to the power half, right? Similarly, if I do not write down a to the power anything, you will assume it to be a possessing a power of 1, right? That's simple. Now what must 10 be raised to in order to produce 1000? You know it already. 10 cube is 1000, so the answer to this one is going to be 3. Now the fourth example, if I write down log 1 base 5, log 1 base 5, now this means that what must 5 be raised to in order to produce a 1? That is going to be a 0. Therefore, whenever you have 1 for an argument of a logarithm, you are going to have an output of 0. Likewise, not really likewise. So, and this one appears surprisingly quite often. And now if I write down log 7 to the base 7, now what does this say? Pause the video, give me the answer. Now it says that what must this base of 7 be raised to in order to produce me a same answer? Of course you know it, that this is going to be 1, so the answer is going to be 1, and this is the result that we use quite often in solving logarithmic equations, right? Now from just 5 examples, we have already discovered 2 facts: that log 1 to the base anything is 0, which is this, and log a to the base a, log anything to the base anything, is just 1. Don't memorize, they fall straight out of the definition. Now the question that students always ask is that why do logarithm laws even work? The laws that I stated here: product rule, quotient rule, and power rules, right? Excellent question. Let's discover them and not memorize them. Now let's say that 2 cube times 2 power 4, what is that? You just add the powers, right? 2 power 3 plus 4, so that the answer is going to be 2 power 7, right? So you know these indices rules. Or if I just explicitly rewrite them, so 2 is getting multiplied to itself 3 times, and here 2 is getting multiplied to itself 4 times. So in total they are adding, 2 is adding to itself 7 times, right? So that's why the associative property in addition for indices exists, right? So everyone knows this. Same base, you add powers when they are multiplying, the terms are getting multiplied, right? Now let's rewrite everything using logarithms. Suppose 2 cube is 8, suppose this is 8, and suppose this is 16, right? And we are not supposing, of course these are the answers. Then 8 times 16, so if I rewrite 8 times 16, that is going to give me 128, right? Now ask yourself, what is, so I can rewrite it as what must 2 be raised to in order to produce me an output of 128, right? Of course the answer is 7, right? 2 power 7 is the 128. So we can write down that log 128 to the base 2 is 7. Notice something. Where did the 7 come from? It came from 3 plus 4. Now 7 is 3 plus 4, and this is log 128 to the base 2. Now what was 3 and 4, right? If I look from here, this is nothing but log 8 base 2. So this is log 8 base 2, and 4 was log, look here, and 4 here was log 16 base 2, right? Log 16 base 2. We had the same basis, so we multiplied the arguments in order to get 128 to the same base, right? So the first rule is log a to the base b plus log c to the base b. The need of this the restriction is that your bases ought to be same, right? You have b on both the sides, so this becomes log a times c to the base of b. And using these indices law only, it's similar that if you are dividing it, it becomes it gets because when you're dividing the two exponents, the powers subtract, right? Therefore this the quotient rule states that if two logs are getting subtracted, then you divide the arguments, the second argument from the first argument, right? So this becomes log a upon c to the base b, right? So this is the quotient rule. And if you have the power rule, so for example, and it is derived from the product rule, which is right here. So if you have a to the power 3 to the base b, now this is what, this is log a times a to the base b, and I can rewrite it as log a base b plus log a base b plus log a base b. And because these are three logs, I can rewrite it as 3 log a base b, right? So the exponent of the argument becomes the coefficient of the logarithms. Very easy. So we can rewrite this power rule as log a to the power r, and base b for the logarithm makes it r times log a base b. So this is the power rule. Okay. So something incredible happened here. Instead of adding exponents, we multiplied the numbers, right? The powers. Multiplication became addition, and in quotient rule, the division became subtraction, right? And similar for power as well. Now, if anyone ever asks you why do logarithm laws work, you now know the answer, because logarithms simply reverse exponentials. We'll prove and use these laws properly in Wednesday's lecture, which is going to be the second in this series. Today I wanted you to understand that why these laws exist. Now let's finish today's lecture with a genuine Cambridge style question, which is, let's say, evaluate log 27 to the base 3 plus log 1 upon 25 to the base 5 minus log 1 upon 8 to the base of 2. Okay. Now I can rewrite all of this as 27 may be written as 3 power 3. 1 upon 25 may be written as 5 power minus 2. And 8 may be written as 2 power minus 3, 1 upon 8. So now I can bring the coefficients back to the coefficient, the powers back to the coefficient, and make them the coefficient of the logarithm. So now this becomes 3 log 3 base 3 plus, sorry, minus 2 log 5 base 5 plus 3 log 2 base 2. Now what did we see here? We saw that if you have logarithm anything to the base anything, it becomes 1, right? So I can turn all of these into 1. So this is 1, this is 1, and this is 1. So this becomes 3 minus 2 plus 3. So the answer is simply going to be 4, and that's it. So it is as simple as that. Okay. Now I hope you noticed it that not a single calculator button was pressed here. Everything came from your understanding. So in summary, what have we learned today in this lesson? Not logarithm laws, not difficult equations. We learned something much deeper. We learned why logarithms exist, right? Why they are the inverse of the exponents. We learned that they are simply the inverse of exponentials. We learned to move freely between exponential form and logarithmic form. We learned that every logarithm simply asks what exponent must the base be raised to in order to produce that argument or power, right? We learned the restrictions of the arguments of logarithms, that they have to be greater than 0. We learned the restrictions on the base, that it has to be greater than 0, which means that they have to be positive, but they can't be 1, right? We did that. And we even discovered where the logarithm laws come from, not by memorizing, but by thinking about exponentials. So when we are doing lecture 2 on Wednesday, our today's lesson was only the foundation. So on Wednesday, we'll use today's ideas. So make sure that these ideas are anchored well into your head. We will use today's ideas to build the 3 logarithm laws properly. We'll prove product rule, which we just did today, but I'll be starting in a lot more detail and in a more clearer manner, right? We will be doing quotient rule, we will be doing power rule, then we'll use them to solve actual Cambridge logarithmic equations. We'll also look at domain restrictions, which we did today as well, by the way, and this is one of the biggest reasons the students lose mark in P3, right? And then on Friday, we are going to bridge everything. We are going to bring everything together. We'll move into exponential equations and linearization. You will finally be able to solve equations like 2 power x is equal to 10, the answer of which, by the way, is going to be log 10 base 2. Put it in your calculator, like log 10, press it, divided by log 2. This should give you the answer of x, and then when you raise 2 by this power, you're going to get the answer of 10. So you can do that. We'll also learn on Friday how to transform exponential models into straight lines. So exponential models go something like this. If you're trying, so if this is y, this is x, they can only be turned into straight lines if you change this, if you shift this to you keep it as it is, but you change this into log of y, right? And then this exponential model, this exponential curve becomes a straight line, right? We learn how to transform them into straight lines, and we'll interpret gradients and intercepts of those and connect everything to ideas you'll later see in differentiation and differential equations. And by the end of this 3-part series this week, you won't just know logarithms, you'll understand why this entire chapter even exists. So if this lecture helped you, please leave a like, subscribe to Easy Talim, leave a comment on how we can improve, and share it with someone who's preparing for Cambridge 9709 P3 with you. Even if you're not enrolled with us, keep following the series, because I'm trying to prepare everyone who's watching it for their October-November retakes this year. I'll continue putting the key ideas out publicly, because understanding math should never be limited to a classroom. Thank you so much for watching. On Instagram, we go by the name of Easy Talim. The handle is written right here, EASYTALEEM. If you have any queries, reach out to me. Feel free to reach out to me on my WhatsApp, +92 329 3028 485. Thank you so much for watching. I'll see you on Wednesday for part 2. Allah Hafiz.